So I think we can start. First thing we should talk about is a couple of features about the model that you will find helpful as you're developing your skills. And those are, first off, the Help tab. So if you go to any model like this one, and you look in the upper menu bar at the top, you'll see a button called Help. And if you click on that Help, you will see an option of looking up something in the dictionary. That's where you know what you want, and you can go look it up. Also, it'll take you to the manual that will teach you, elaborates different large-scale programming tasks. But by far the most helpful one is this NetLogo dictionary. So if you click on that one, that'll take you to a page that is extremely helpful. First thing that you'll notice is that you have different ways in which this dictionary is searchable. We're going to talk about commands that you can give the agents in this world, and those commands don't work universally with all agents. For some agents, they have very specific commands. For other agents, they have very specific commands, and you can't confuse those two. So under the first gray bar, it says turtle related, right? So turtle related means all of these procedures that if you assign them or request them of one of these agent types, turtles are the mobile agent types. You can use any of these procedures with those. All right? Second, patch related or patch only. Actually, this will say turtles only, or turtles related, patch related, link related. In your model, if you try to use one inappropriately, it will tell you that whatever you're doing is a turtle only command, so you're wrong, you can't use it for a patch in the landscape, and vice versa. It'll communicate that to you. And simply what that means is you're using a command that only is here, but you're trying to apply it to a turtle. And the program is smart enough to catch you doing that and tell you, sorry, that won't work. Okay? Last one is link related, and I haven't taught you anything about links. Links are a thing unto themselves. They're also classified as an agent. But if you look at the various kinds of commands, you'll see that they're very different. That's because their properties are all tied to establishing a relationship between two turtles, right? And so this here can be things like a vector. It can be a simple length. It can have a certain strength so that it actually pulls a turtle together. It acts like a rubber band, and so you can't stretch them apart. Think about relationships between two siblings and their mother. Some are closely attached to their mothers, and they don't want to go very far away, whereas others aren't that attached and therefore will wander very far away. If you model the relationship of two siblings to a mother, you could give one a rubber band type of relationship that only stretches so far. And that will prevent that daughter or son from moving too far away from the mother. If you were making a model of family dynamics, how families interact with each other, that would be important. A good thing to try and do. So that's how links operate, and very oftentimes you'll be talking about a link in terms of its connection to this turtle here and its connection to this turtle here. If this is at coordinate 8, 4, and this is at -3, 7, right, then the band is defined by those coordinates. So they're different from the other agents from turtles. You will learn about them, but that's the next level of programming. Otherwise, down below, you're going to learn about something called agent sets. These are subpopulations within the overall population. We'll talk about color and how to use color, logic and control flow, and a whole bunch of other, here's the mathematics. And so essentially this tells you what are the math operators and the relationships that these are things you can use. These all count as the primitives built into NetLogo. Now, this is where you don't quite know what you're doing and you're going looking for something in here, these 3 levels. So, you know, I kind of want to know, I'm trying to figure out how I can identify what is happening right in front of me, one step in front of me. And so I say, I want something like that, and I look through the turtle categories and I see one called patch ahead. Now what I do is I can click on that, and that will immediately take me to the place in the dictionary where this particular command is located, and then it will tell you what it does, as well as give you some examples of how it can be used in code. So, first thing to notice is that it has a turtle right here, which means it can only be used with turtles. Secondly, you can read the definition, reports about a single patch that is a given distance ahead of this turtle. So the turtle is always facing in a certain direction, and if you type in patch ahead at a certain distance, it will look for a turtle there and tell you about that turtle. That is, along the turtle's current heading, reports nobody if it can't find anybody there. So here's an example of code. Ask patch ahead, 1 step, set the P color, set the color of the patch green. So it'll look ahead 1 patch, and it'll turn that patch ahead the color green. Real simple. And then down below, you'll see some comments about how it's operating. So, and then it also, here it'll refer you to some related kinds of operators if the ones that you have here, if patch ahead turns out not to be what you want. You're going to spend a lot of time in the dictionary, fishing around, trying to find. The only way to really get good at NetLogo is to use it a long, long time until all of these commands work their way into your brains. Who else here, anybody here, you program Python?
Yeah.
And Python, how long did it take you to get good at Python?
I can know all the basic operation because we have other programming language classes, but the usage of those libraries, we don't usually remember it. We just search how to use them on the internet when we need them.
Much of NetLogo and these primitives are exactly the same way, and this is your method for looking things up. Over time, you get good at this by making model after model after model after model, and you begin to learn, develop a feel for what commands are, what they do, and even if you don't know how to solve a problem, you know how other people have solved a problem like this in the past, and so you have a kind of instinct about how you're going to accomplish that. It comes with time, and so at the beginning you are going to be looking up lots of things. You will have an advantage if you have programmed before, because the logic of programming a lot of times is very, very similar. It's just that there are different languages with different syntaxes and different terms. but the way in which they operate are very similar. This is slightly different because it's multi-agent as opposed to a single agent that the program is executing on behalf of. Okay, and then last but not least, if you, for convenience sake, if you stumble across a command, a primitive used in a piece of code, probably most likely from somebody else, and you can't quite figure out what it's doing in the program, then you have this lookup at the top where everything is listed alphabetically. So you look for something like random. You're going to learn about random. So you click R, and the first heading is random, random float, random exponential, random normal, random px coordinate, py coordinate, and so on. You learn about all kinds of randoms. Some of those you're going to be learning today because that's one of the more important features of this. So you also have the ability, if you know what you're looking for already, but you don't understand it, you can look things up this way. So there are multiple ways in which you can use this dictionary, and believe me, you're going to end up using it a lot, right? You're going to have a subset. I think when I was reading, getting ready to come here, and both the last time to Taiwan and this time, and I've always wondered how it is possible, how many characters a typical Chinese-speaking person has to memorize. And I read things like there are thousands and thousands of them. And so do people really learn thousands and thousands and memorize them? And it turns out it's the same in English, that you use about 600 characters. And the other ones you might know or you could look up, but you get most of life's work done with only about 600. Same way is true with English. We only use a certain number of English words. There are, of course, lots of others, but no one uses them or says them. So the dictionary is going to be the same way. Over time, there's going to be a subset that you use over and over and over and over and over again. And you're going to know that. It's going to become automatic. And a lot of the other ones are going to be more obscure words that you would have to look up in order to understand. Okay, back to PowerPoint. Oh, that's... Okay, so we talked about NetLogo library. And here are the last parts so that I can get you familiar with NetLogo before we actually start learning some outright commands and start actually programming. The first one are the interface devices. If we go to NetLogo again, all the interface devices are hidden under this particular tab right here. You can see it. By default, it starts on the heading button. Okay, so if you open that up, it has a whole range of devices that you install on the interface. Let's make it bigger. So you can see you have something called a button. Actually, what these three things are buttons. And you have a slider. This right here is a slider. That little red button slides up and down. This is connected to a variable, and at the outset, that you can tell your program how many of this thing do you want, so that you can actually change the coding, the program, by using the slider. You have on-off switches, which turn on parts of your code or turn parts of your code off. You have a chooser, which actually makes choices between different options in your code. All of these have unique ways of programming them. You have an input monitor, you have a plain old monitor, you have a plot device, you have an output box, and then you have the ability to put notes. You could write a note right in here yourself about this program so that any user could read this right up front on the interface. So you're going to use those devices as we go, but that was important for you to see that. These are all just devices that you use. Now, every one of these has a specific kind of way to program them. So if I drag over setup and I hit edit, it opens up a window. This one's very simple. The command for setup is setup, and the button is called setup. If you go down here to this one and edit that one, you'll see that the global variable this stands for is the total population of a certain kind of agent in this world. The minimum value it has is 0. The maximum it has is 200. And it goes up and down in increments of 1. You can reset this between 0 and 5, between 100 and 1,000. It can go up and down in 0.05 increments, whatever you want, whatever is necessary. So for example, right now, if I move my slider up to 200 and then I hit setup, look at what's in there now. That was set up for 50. I've now told it I don't want 100 of these. These are hunter-gatherers. I don't want 100 hunter-gatherers. I want 200. Whoops. Do I have go on? Oh, I do. So I'm going to close that one out. It changes the number of agents on there. I don't want to go through opening up again, but that's the kind of function that those have. Another device that you have that you're going to find very helpful is something called the inspector. Inspectors are little boxes that you ask to pop up on the surface of your model that will give you a very concise report about a specific agent in your model. So I'm kind of curious about that agent right there. I want to know everything about that agent so that I can figure out why is it doing what it's doing. All I do is hover my cursor over that agent, click on it, right-click on it, and go down to Turtle 1. That's a turtle, even though it's shaped like a car. I changed its shape. Click on it, and I say I want to inspect Turtle 1. That will open up a dialog box that will tell me everything that's going on with that turtle. So it tells me its number, its assigned number is 1. These are all built-in variables. Its color is color number 15, or red. It's heading in a direction of 353 degrees. It's on an x coordinate of 14 point something something, y coordinate 5 point something something. So if we go x from here, 0 to 14 up 5, that roughly makes sense. It doesn't have a label at all. It is a turtle, and it has hidden is a value that you could give to it false, which means nothing. Size, it's 1. Pen size is 1, and the pen mode right now is the pen is up. When you were drawing those spirographs, you put your pen down. So on those, if you were to look in an inspector, you would see that that turtle has a pen down so that it's drawing, right? Called pen down. So that inspects everything about it, but you can also inspect patches. So I clicked randomly in the green field, and I'm going to inspect that patch. It's not going to have much going on. It's going to tell you what its coordinates are, and it's going to tell you its P color. What color it is 55, which stands for green. I'll show you about colors and other things in a little while, and then the rest are irrelevant qualities. So these are variables that describe an agent in question. The values that you're getting there, right, that's an agent. Now, if I were to describe that agent and ask myself, what properties does this agent have? I might have a variable for female. I might have a variable for age, 22. I might have a variable for height. I don't know, what's height in centimeters? I'm used to, so 5'4" in inches, or 5 feet 4 inches is what in centimeters? 124? 154. 154. So variable age, height, maybe one other thing, occupation. And which means her job. Her job is to be a car, right? So all of those would be what we call in programming, we call those properties. And all the agents that you have in your world are going to have a set of properties. When the landscape or when other people interact with that agent, one agent to another, it's the fact that you have different properties, and those different properties all have an impact on another agent, that this agent changes and his properties change. Or maybe they don't. Maybe this has no impact on this. Maybe this is influenced by certain features but not by other features. That's what gives this program the ability to model complex social interactions. Because every one of these turtles has a set of properties and the ability to interact with other agents and change themselves or change others, just the way humans do in social relations, just the way in which animals do with other animals, or animals and humans, or in landscapes as well. That's why this is such a helpful platform for modeling. Okay, so you always are capable of looking that up. Essentially, you right-click on any agent, go down to Inspect, and if it's a patch, you inspect the patch. Notice here, when I clicked on the car, I'll click, and I have this patch, which is underneath it, and then I also have the turtle. So I have to specify which of those two agents right there I'm curious in understanding. Okay, so you have inspectors. All right. Last one, I'm going to call commenting out. I don't know how it started. I'm not sure where the origin of it is, but it has become convention that in your code you leave comments for other people to read when they're trying to understand what your code is doing. If you get lazy, the code, which looks very understandable to you, you might say, oh, that's so obvious, I don't need to write any comments in it. And then your professor ought to go like that and say, you're being lazy, comment your programming, comment it out. So in a program like, okay, now you're going to see in there, you notice some coloration here, all of these things. When you have colors like that, that tends to mean that you got something right, that this is a term that's in the dictionary that it recognizes. If you didn't get it right, it'll tend to be black or gray. And up here, like say let's just say I misspell something, like I leave I leave the A and T out of patch. And I want to check whether or not my code is right. Well, first off, notice it turned black. It's no longer this kind of purple color that the other patch words are. That indicates that I've got a mistake. But just to be sure, if I ask it to check my code up here, look at it. It goes right to the spot and says, nothing named PCH has been defined. It doesn't have a definition in the program, but patch does. It's a primitive. So now if I check it again, it says perfectly fine, and that turns back to a different color. All right, so that's one of the ways to check your programming, to figure out where your mistakes are, so on and so forth. Now, commenting are grade terms that are typically preceded by 2 semicolons, right? If I eliminate those semicolons and just leave it like that, it is going to flag that as a huge mistake right away. Creates turtles. It says, nothing named creates has been defined. You're right? That's a mutation word. It doesn't belong here. So if, however, I hit 2 semicolons after it, then the program ignores. That's essentially what those 2 colons mean. Ignore everything after it that comes after it. Don't worry about it. That's for humans. Machines don't need to know this, is what that means. Right? But it's really useful for humans. These are really simple examples, but still, CRT 100, what does that mean? Well, it means to create some turtles. Over here, this code right here says it's commented, distributes 25 turtles to the 8x8 patches using their WHO number, that number right there. So that's a comment. And essentially, by the way, even you are going to be happy with this because you're not going to finish a model, a bigger model, in one night. You're going to work on it, then you're going to go to bed, and you don't get back to it till 2 days later, and then you look at it and you go, I have no idea what I was trying to do, right? Whereas if you leave a note for yourself, you'll remember, oh, right? Or you'll say, God, why am I trying to do that? This would have been so much easier. And it'll come to you at 3 in the morning when you will be half awake and visualizing code in your sleep, right? Mr. Programmer, do you code in your sleep?
No.
You never code in your sleep? Ever? Once? Not once?
No.
I've had dreams about coding.
Terrible.
Huh?
That's terrible.
No, it's supposed to, well, for one thing, this is true. You can never read while you're asleep in a dream. You'll look at it and you'll try to understand it, but it makes no sense to you. You can't read words off a page. So same thing with programming. You'll be coding, but you have no idea what it actually says. And that's never happened to you? Would it scare you if it started happening?
I code to sleep, but I never sleep to code.
A good philosophy. Okay, so that's what commenting out is, or commenting. Documentation, which is different. Documentation is the things that you put in here, in this page. Remember the info page? This is how you document your model. These are kind of meta-level comments. Whereas in here, you write specific statements about what a piece of code is supposed to be doing, so that future people who come to look can follow you step by step and understand your thought process. Okay, so at the end of the last session, we had worked through 2 models I call those spirograph. Any of you play with a spirograph when you were a kid, right? You draw these geometric shapes. It's really all premised on math, right? Well, that's what you're doing now using computer code to design that. And if you remember, the third exercise was to distribute the turtles that you make. So open up NetLogo right now and make sure that first step was to create 100 turtles. Then I would go to setup, go to the interface, click on setup, and see if you have a stack of turtles at 0, 0. You all should. Almost impossible to make a mistake, but it's worth checking. This is worth doing later, getting into this habit of checking as you go along, frequently saving, clicking that check button. It helps you get along. So the first thing you're going to do is create a stack of 100 turtles. There. So right now, I have a stack of 100 turtles sitting at point 0, 0, right in the middle. Now, I want to move 25 of those turtles to each one of these locations. And those are some permutation of 8. 8, 8, 8, negative 8, negative, 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 positive. Okay? How might I ask these turtles to go to these locations? Well, the first thing you're going to need to do is to identify 25 of these agents that are all on the spot 0, 0. You need to identify them so that you can talk just to them. Right? One of the things, let me go in here, is that these turtles, I'm going to right-click on it, and look, there are up to 99 turtles sitting there in the stack, right? Starts at turtle 0 and goes to 99. Now notice every turtle has a number. That number is assigned to the turtle based upon when it was created, right? So turtle 0 was the very first turtle created. And that turtle number is an ID. It's an ID, a property that is unique to that turtle. So you can always identify turtle 0 by asking turtle 0 to do something. All right. That is called, when you're programming, that is called its who number. Who, turtle 0, turtle 12, turtle 99, right? So every one of them has a number. Okay, so I have to ask 25 of these turtles to move to one of those 4 coordinates. Now, we're going to try this by using something called pseudocode. Pseudocode means that you try to speak the way this programming thinks, but you don't worry at all about specifics of the coding language. You just try to say in words what you want to do. So far, we're going to send them from here to over there. What do we want them to do? Hey, turtles! Right? Which turtles am I asking? I want any 25 of them, so how do they decide? If I just go, hey, turtles, they're all going to look at me and want to know what to do, when in fact I only want 25 of them to pay attention. So what do? How do I get only 25? Well, how are they identified? Huh? By their call ID, their turtle number, right? So we have turtles, 0 to 24. Okay. Hey turtles, 0 through 24. And by the way, hey is, when you go hey, you're actually saying ask turtles who have the who numbers of 0 through 24. And then that's the address. That means something like, hey Fred and Dolma. And those two look. And then I say, do this. So in this block here is the command. Right? And what's the command? Remember, we're using pseudocode, right? We're asking a number of turtles, specifically the first 25 turtles that were created in this world, to do what? Just use your everyday language. What do we want them to do? Move to. And it turns out that NetLogo has a primitive called move to. And where do we want them to move to?
Position 8-8.
We want them to move to 8-8. Okay.
Do you need any period or space between 2-8?
No. You don't divide the coordinate systems are not divided. They're just 8-8.
Just 8-8.
Yep. Or 7-5 or whatever. And as it turns out, you got it mostly right. Look at the way in which it's programmed here in this particular one. Ask turtles. See, notice you could, I'm going to ask turtles 0 through 24, when in reality, it would be much easier to say, hey turtles, if your who number is less than 25, I want you to do this. So I say, ask turtles if your who number is less than 25. Can you read that? Okay. Ask the turtles if your who number is less than 25, move to patch number 8-8, located in the upper right quadrant. Okay, so we got 25 to move. Now suppose we want to ask the next 25 to move. What do we have to do? Ask turtles if your who number is greater than or equal to 25, and your who number is less than or equal to 49, essentially that's saying you're the next 25 in the list of the groups of people that were made, then move to patch 8, -8. Do you see the logic there? How it's working? And you continue through it. Ask turtles if who number greater or equal than 50, less than 74, move to 8, -8. Ask turtles if who is greater than 75 and less than 100, move to patch -8, -8. That should set everything up to position those turtles at those 4 center points in the quadrants. And so, if I now go, well, first off, let's check the code. So my monkeying with it didn't seem to break it. So I'll go to the interface and I will move them. And now I have 4 stacks of 25 turtles in each of those 4 quadrants. Okay? Everybody get that? Is your model okay? Now, it comes time to drawing the flowers, which was the assignment there. And it's very simple. Remember, there was that first step of putting your pen down so that it draws. Then the second step, in the earlier model, we moved it 4 steps and we turned it 30 degrees. Now in this one, because we've divided our space in half by moving them, we have to cut down the forward command, forward steps, by half. So we move it down to 2 and then we tell them right turn 30. Right? So up here, the setup, remember what that is doing is it's initializing or building the world that these turtles live in. And then the to go is basically live your life in this world now. The go command, it will go through a sequence and then repeat itself, go through another sequence, going over and over again. That's the meaning of the word iteration. It will iterate over and over and over again. And you want to think about each one of those iterations as what NetLogo calls a tick, right here. And a tick is a unit of time. So you've built a world, that's the setup. Then you build a set of behaviors like move in this way, and then you say live your life. You click go and your agents follow their life dictates. That's what your models are going to be. You're going to build a world, whatever the setting is for your model, complicated or simple or whatever. You're going to tell your agents, this is the world you live in, deal with it. Then you're going to make your population, and you're going to give it certain qualities or properties, and you're going to tell it to act in certain ways. And then when you push go, you're telling them, all right, people, live your life. And after, say, 50 years, you hit stop, and you say, look at how the world has changed, and look at how these agents have changed themselves. What does this tell me about the dynamics, the way things operate in the world I just built? And that's the value of the model. All right, everybody got their model all set up? Push go. Once you have all this code in, pen down, move forward to right turn 30 degrees. Turtles move in a pattern of 2 steps with 30-degree turns. I was a good boy. I commented. Once you get all of this into your program, give it a try. Are you okay? Oh, now you only have 1 there. You got to get some to go there, some to go there, and some to go there. Look up here what we have. Ask turtles if your who number, if your identity tag is less than 24, go to the first one, 88. If your who number is less than 50, who number less than 25, that's right. If less than equal to 25 and who, look here, you got less than and less than. That's why it's not showing any of those turtles, because there are no turtles that way. With that, that's a mistake, but it's a mistake that NetLogo thinks makes sense, and therefore it's not flagging. There you go. How about you guys back here? You okay? You okay?
Teacher, I forgot.
What's that?
last week,
Oh.
The last models we use.
Yes.
So can I ask you
Yeah.
which models?
Okay, this is a brand new one.
Brand new one. Oh.
Yeah. So what you want to do is open up that, what I call the shell simulation in your, in the folder for this class. Okay, there will be something, support documents. Then look under typical simulation shell. So you want to download that to your computer, bring it to your computer, and then double click on that and it'll open up. Okay? Yes, that's the empty shell in which you build all your models. Yes. Okay, so now go to your programming tab, which is, I can't see. Oh, here, wait a minute. You should have 3 tabs.
Here.
Up here, I'll show you on mine. You see up here, I have interface, info, and code. Do you have those? Okay, you want to hit on the code tab, click on that, and then that should bring up that, and that's a shell. So the first one is the Go, and that's where you put all of, let me show you. I'll pull that down a little bit. That's where you put all of that. Okay, so all of that goes in to that first part. And then under the to go command, which are the procedures the agents are going to operate by, you put this. Okay? So if all goes well, you should have little flowers in all 4 corners that look like that. There, if you slow it down enough, you can see each individual agent circling around over and over again. It's living its life. It's very simple. It just moves, turns, moves, turns, moves, turns. That's all it does. Its entire existence. And yet it's happy. It's a simple life. So these are all simple drawing exercises, but you're learning commands and logic patterns by performing these different drawing tricks. So it's important to get these to work for yourself first. Yeah.
Check which one is
Oh, you're throwing an error. End expected. I know what that is.
Yes, I think coding might be something like wrong in the coding.
Yep, it's a syntax error.
Oh, okay.
What it means is, where is it highlighting?
And expected.
Click that again to check. All right, now scroll down. I'm trying to see what it's highlighting.
Actually, here. Is it?
Yeah, why is it highlighting that? That doesn't matter. CA,
It's
create
my-
terms 100, let me see. Because I know why you would get this
Okay.
command
Move to patch F88
to go.
2020.
Put your tick, first off, put your tick down below. After the procedure. So remove that and put it at the bottom. That always goes last. Okay, now ask turtles, pen down. Oh, there it is.
Oh, this one is wrong?
No, wait a minute, you're okay. Forward to, because there's your closing. Check it again.
Oh, still.
Okay. All right, CA, create 100 turtles, right? Ask turtle if who, then move to 88, good, bam, bam. Bam. Reset ticks. End. To go. Ask turtles, put your pen down. Move forward to. End expected. But then it goes down to this and highlights that.
Do we need to remove this? I don't know.
Okay, for this one we can, but that shouldn't be doing anything. It likes it now. Oh, no, end expect. Oh, now I see what it is. You needed here that. No, you shouldn't need that, actually, because you have that, and this is not a turtles. I thought maybe it was that. End expected.
What does it mean? Something
I
wrong
don't
with the
know.
coding?
I'm trying to figure it out. I don't see anything
Maybe
wrong with
something
your coding.
Space or
No, I put a space like between that and there for legibility, but it's not, it doesn't matter. I can't see any that you made any mistakes. Do you see a mistake in there?
Not yet.
就是看不到它发生什么事。
End expected.
What here? There is supposed to be an end.
Oh, that's what it is.
What's that?
That N got deleted.
oh,
There should be a two end block.
Yep. Okay, now you should work. Give it a try. We'll see. Check. Now go to interface. That's a go once. And then this is go continuously.
Okay. Thank you so much.
Yep. Yours is going? You helping her? Okay. So that was the third one. Exercise 3. Exercise 4. Okay, for this one, I'm going to show you the model and how it works. And then you guys are going to have to program it without any help. Right? All this is a little more complicated than the previous one that you just did. So remember what you did for number 3 and try to implement it for number 4. Okay? Now, one difference is I've got a stack of turtles in the center still. And if I click on that, notice I have that many turtles there. If you look here, I have that many turtles there, and so on. Now, watch what happens when I hit go once. Set up and go. So I've changed this. The two big changes are, one is you want a stack of them in the center as well as the 4 corners. And then second thing is you want square petals, not round petals. How are you going to do it? You get to do it on your own. So hopefully some of you are making progress. The best way to do this would be to make a copy of the earlier model, and all you have to do is tinker with that one some. If you're first off, remember, if you're putting 25 turtles on all 4 corners, plus you want 25 in the center, how many turtles do you have to start with? 125, right? Not just 100. And then the second thing is, you really don't need to do anything about 25 of those turtles. You just have to move the other ones in exactly the same way that you moved the other turtles for making the circles. The distance is still going to be 2, and to get squares, you divide by 90. 360 is a great number because it can be divided in, it has so many factors that you can make all different kinds of shapes of objects there. Yay, you got that one. Make the number of steps it takes, give it a little more. Go to 3 and try it, go to 4 and try it. See what the best size is. That's the size. Now, the one thing that is missing is that you didn't have in the middle. See how we put turtles in the middle? So we changed it one extra step. First off, think about your problem is that you were moving 25 turtles to each of those 4 corners, right? Now, how many turtles did you make to begin with? When you say create turtles, how many did you create? You want to make 5 locations, right? But now go back to the original, the very first thing you said is you wanted a certain number of turtles in that world. And you start that by CRT, create turtles. How many turtles did you make? You have a number there. See here when you create turtles? You made 100, right? Now, if you have 25 turtles at each one of those 4 locations, and you only made 100 turtles, how many does that leave for being in the center? 0. So you have to make more turtles to start. Since you're working with 25, you should probably make 125 turtles. Yeah? All right. Oh, to go to 0, 0, when you created your turtles, all of those turtles, they were already on 0, 0. The moment they're created, they go to 0, 0. So, as a result of making more turtles, you asked all these other turtles to go in a bunch of different places, and then the extra turtles that are left over, they're going to be in 0, 0, right in the center already. So now try hitting just go. Or you don't have to move those turtles at all. So now hit, and then go. Way to go. All right. No, you're still working? Almost.
Ask to 不需要偏档哦。
Pen down.
Pen down.
Yep. Forward 2, pen down. Yep.
Forward to.
Forward 2.
And
Right turn 30.
1 to 30.
Yep.
1 and
No, there's something going on there in that piece of code. You don't need any of that. So, forward 2. And then right turn 30. Close brackets, and then end. That should be good.
and if it ticks is 12.
And if the ticks go to 12, then it tells the model to stop.
I write this.
Okay.
And stay up, go. What's wrong with this?
You know what? Your pen isn't down. Right there. You got to put pen down.
Oh, pen. Oh.
and then pen down.
Okay. And pen down 4-2.
And then forward 2 and right turn 90. So try it.
Oh, it works.
It works. See? I wouldn't tell you something that didn't work. Okay. We're going there. Everybody's basically done? Yeah? All right. Now, what I want to show you is something, how one little small change to the model can have big consequences. This is going to be really interesting to you as you're building your model. You might change things in one small way, and yet the consequences will be profound. Think about that when you are working on your problem. You make one small change and suddenly everything about your model changes. The example I've been using is Tibetans and the jobs they take, right? Maybe the one thing that's a really important factor is whether or not they are male or female. And suddenly your data, as a result of including that part in your model, which is only a very small part of a much bigger model, causes all of your data to suddenly fit the data set that you have from the real world. And that when that happens, you go, oh my gosh, it's the sex of the person that has the most profound effect upon what jobs they take. And you suddenly discover something. And modeling is like that in the sense that you can genuinely discover things that you wouldn't have known had you not been using a computer. Because a computer can figure all this out for you, whereas it can get lost in the haze of all the things that you're trying to understand. So I want you to change one thing about this model, and that is you add this little bitty piece of command, of code. Just that one little request, right? I hope you can see what it does. It's saying here, do what you've been doing, and then do it 4 times, and then turn, after all that's done, just 10 degrees. Turn an additional 10 degrees. You've been doing all this time, but at the very end, take another little step to the right, right? So go around, do it 4 times, that makes a square, and then take a little step to the right. Then do what you've been doing all this time, but then just take a little bitty step. And what happens in your code, right? So this was what it looked like. And it's a little bit boring. If you see, the turtles and their colors just keep repeating themselves. But I've broken the repetition loop by telling them to skip another small, just a little bitty 10 degrees. And suddenly it turns from that into that. See what I've done? I can do it. I can do it just once. So click go, and then click again. Remember, it's done all of that, and then I told it turn 10 degrees off your trajectory. So scoot a little bit in a slightly different direction. Now do it again. Scoot 10 degrees after that. Do it again, do it again, do it again. And then just do it all the time. And you actually kind of get an optical illusion. That little piece of extra code, just add a little 10-degree skip at the end. So that's just a real simple example of small change, profound consequences. Everyone get the little spinning wheel optical illusion? It was just that little bitty code change, right? Right turn 10 additional degrees. There you go.
Can this be accepted?
What?
Can this be accepted? It looks like a little bit thicker.
Yeah. Oh, that doesn't matter. I know you probably, do you have steps forward 4 or forward 3? That's all it would be.
Same code.
Everything's the same, and then forward how
This
many?
one's a different.
Okay.
Forward. Same.
Yep. Okay. All right. So now we're going to talk about the book and the chapter you had to read. So I'm going to tell you what I think is important in this chapter out of all of those things. I want you to read, challenge yourself to read before you come to class and understand as much as possible. And then in the class itself, I'll spend some time talking about the points that I think were most important, and hopefully between reading before you come and then me doing that, we'll end up with a pretty good understanding of the chapter. These chapters are going to be about the more abstract level of modeling, not these little, all of the programming itself is going to be understanding the language, being logical in breaking down your problem. That's what a lot of computing is learning to understand logic, right, and being logical. And then the practical processes of building the model. All of those are hands-on, and they're tinkering, and they're solving very concrete problems. But there is a more abstract theoretical level that this book talks about. And so that's what you should expect from the book, beyond the practical stuff that we learn here in class. And the main question of this chapter was, what are models good for? Why would you want to build models? How can they help you? And most importantly of all, when do you think you ought to use one? And when would it be possible for you to use one, but it really won't help you any? Because not everything will actually benefit from you building a model about it. Some things are ideal for modeling, other things, it really doesn't make much sense. You could do it, but you're not going to get much profit from performing it. So, first, defining what an agent-based model is assumes that many, if not most, of what you experience in the world, that it can effectively be explained or modeled with agents and an environment and some description of how the agents in the world interact with each other and how those agents interact with their environment. All you have to know is the world they live in and the kind of people they are and how they relate to each other, and you can explain most social phenomena. You have, in an agent-based model, a little army of autonomous entities. Every one of those entities that you create is its own little being. You literally should think of them as little people moving around in the world, acting on the basis of their properties, the variables we were talking about here, the rules of their conduct, and sometimes you give these agents goals. You'll tell them, hey, I want you to accomplish this. You figure out how to do it. Every one of the agents in the world, you can design that way so that they have certain personality traits, certain ways of acting in the world, and certain potential goals. For example, if you had dogs and humans in your world, both of them are agents, both of them have properties like the sense of smell that a dog has is thousands of times better than humans have. And then you have behaviors. You can reliably expect that dogs will use smelling their landscape as a primary way to navigate in the world, whereas humans will not. We are visually oriented, and we will orient ourselves in the world visually. The environment, this is really important. A landscape in which you exist, which encodes information, and that information is rich, distributed, and exists in varying ways. That is, it is spatially encoded. Let me give you an example. Suppose the campus here was one of these checkerboard landscapes. In this world, there are some parts of the world with long, flat pieces of bricks or concrete, and others with ground and grass growing. If you could break those up into chunks, and you had one block here with grass growing and one block here with concrete, each one of those encodes, carries within itself information. Most of the time, that information you know how to interpret. Okay? For example, suppose it rains equal amounts on the blocks that have grass and the blocks that are cement. What do you know about the grass and the concrete in terms of the water that falls on it? You all know this. It's not I'm not trying to trick you or anything, but that these patches where you step carry information. Where are you going to walk if it's raining? Are you going to walk on the concrete or are you going to walk on the grass? On the concrete. Why? Because what? Compared to the grass. Grass gets wet and holds the water. Concrete, it drains off. Therefore, you infer, or one piece of information is, you know, in a natural world, concrete straight line paths don't exist. Therefore, somebody, probably humans, made it, and they at some point in the past poured concrete in a liquid form, it hardened, and water can drain off of it because walking in grass is inconvenient. All of this is information encoded in your landscape that's very rich. Suppose I walk into a neighborhood and suddenly all the signs, as you walk around in this landscape, all of the signage is in Arabic. And then you cross the street to the other side, and suddenly all the language is in Hebrew. You have two different squares or patches in this world, some of which contain the variable Arabic writing, some contain the variable Hebrew writing. And then maybe in a third one, they contain both Arabic and Hebrew signage. What does that information tell you? Over here, in the Arabic part of the city, where all the signs carry encoding, language equals Arabic, that tells you what probably? Arabic-speaking people live here. Iraqis, right? Or Palestinians. Over here, Hebrew, Jews live in this space, right? Over here, it's a mixed neighborhood, right? The population is mixed. You know that, and as an agent, you're walking through and you're keeping a ticker in your head about Jews and Arabs and how densely populated they are. If you go over here and you see no information about Hebrews or Jews, then you know, well, this is very densely Arabic. Or if you go into and only see Hebrew language, this is very densely Jewish. And in a mixed environment, you have a mixed population. And you can derive all kinds of inferences from this information. But there are also some places in your world that are completely devoid of information. They're empty. They communicate nothing at all, right? So like when you're on a highway and there are cement walls on either side like this as you're driving, those are there to stop the noise, but that landscape is completely devoid of distractions because they don't want you to be driving and be distracted. So they throw no information at you, right? Information in the world that you collect and use for your various purposes is unevenly distributed around the world. You have to go find it. It's not everywhere. It's only in certain places. As a result of this, for you to find that information, you have to go to it, you extract it, benefit from it, it changes you, enriches your mind, and you might do something back to this space to show that you've interpreted it well. You modify it slightly so that now it has a record that you visited it. These patches here, for example, can keep track of how many times you've been to that spot. Every time you go, it adds another tick to the counter, right? Jack was here 12 times last week. This week, 13. It can keep track of that over time. And therefore, both add information. Oh, and by the way, I'm an agent, and I go over to this patch where Jack has been 12 times, and I say, how many times has Jack been here? Jack's been 12. Oh! And then you go back, and that changes you, right? In terms, and your thought process about Jack. Next, these are a set of 7 principles why models will help you, how they will help you. And this is going to be important for you to think about how you want to use models for your studies. The first example is that models will always help you think. They will always force you to describe the world in simplified forms. They identify the most important features of the world that you are studying and will find a way to illustrate the basic dynamics of that world. By definition, a model is a simplified interpretation of the world. Social scientists know that the world is noisy, statistically noisy, and complicated. And you're interested in finding a specific signal in the midst of all that noise. And your problem is to ask yourself, how do I isolate that? Right? A model is a simplified picture of your social group that makes you think about what are the key features that you need to think about. Or put it a little differently, what do you have to pay attention to, but also what can you ignore? Probably more important for your research is not just what you are going to pay attention to, but also what you can forget about. Sometimes when I have students that are working on a complicated research project, they will have, I want to study this. I say, well, what is it about it that you want to study? And they'll say, I want to study this. But then there's this too. But then there's this too. And this. And we got to do it all. Right? And the result is that it becomes such a muddled, complicated kind of thing. Chances are they're not really going to learn much of anything about it. all they're going to do is create a lot of noise that's very hard to interpret. Models simplify the world that explains what pushes this box. Kids shouting is the most important thing about this. Or all kids wear shoes, or something else about that group. How do fish know how to school when they swim around? Why do they swim in those patterns? What are the most important driving features of those scenarios? There's a famous observation from a statistician. His name is George Box. He's British. And he said, every single model that you make and all models of the world, if they're mathematical, physics related, anything else, all models of the world are wrong to some extent. But some of them are really useful. And he means by that, they're really useful to help you think about things, even if they aren't perfect. And then you might add this other line to it. You know what? The only perfect model of the world is the world itself. Everything other than that already has lost some information and is inadequate to the richness of the world. The trouble with the richness of the world is that you can't interpret it. It's overwhelming. Number two, models help us explain what we see by trying to discover the mechanisms driving change, right? You all know what autism is? You know the disease, it's a genetic disorder, autism. One of the consequences of autism is that it makes a person, the term in psychology is mind blind. In other words, they have no way of conceiving that people have intentions. That is, that they have goals and they're trying to do things. So, if you were watching me and I go like this, look out, and go like that, you all have ideas about what I'm doing, right? You will say something, and it's going to be about the goals that I had. I ran over there, grabbed the doorknob, and looked out, and then came back in and shrugged. He must have heard a knock at the door, right? So you knew what I was thinking. An autistic person does not know what I'm thinking. If you ask an autistic person what just happened, autistic people, there are different levels of autism, but certain levels of autism will say, the person at the front of the room moved over here. The person at the front of the room then grabbed the silver object. The person who grabbed the silver object then pulled on this. Then this person looked outside, they came back, that person came back over here. A completely adequate description of what I was doing, except it missed a whole layer of significance that because they do the part of their brain that is used by most of us to think about intentions doesn't work in them, right? So, it used to be 100 years ago, autistic people were poorly treated because their mental disorder was not understood. There was something wrong with them and deficient and judged in a moral way. They were socially lower than the rest of us. But now we know that that is caused by a specific neurological developmental thing in their brains, and therefore we do not judge them, other than we try to figure out how do they see things, and how am I going to communicate with them such that they actually understand what I'm saying. I know, for example, if you're related to someone that's autistic, I know if I say he wanted to go and see if anybody knocked at the door. If you say it that way, he probably won't understand. But if you say he heard something at the door and so he walked over to investigate the sound, I give a physical description, suddenly he understands that perfectly well. So you always have to ask, what's happening in this flow of information that drives it? In order to, someone makes a phone call, but then nobody picks up. Why don't they pick up? Right? In the United States, we use the term ghosting. Do you know what the term ghosting means? If you have a friend and you've been texting and calling all the time with each other, and then suddenly your friend doesn't respond to your texts and doesn't call back, just disappears, goes silent. That's called ghosting. Someone has just ghosted me, right? So I call and no one picks up. They're ghosting me. What did I do? Well, that's one possible causal mechanism. Are there no other possible explanations? What happens if the ringer on their phone is turned off? Or their phone has been broken and they can't afford to get another one, right? Is it turned on? Well, yeah, it's turned on. So if yes, then the phone must be ringing. They see me and they're ignoring me. If it's not, right, it goes to voicemail. Someone picks up. And then you go on and on through this. Every one of your models is going to be like this. And you are going to have to think about not just is the ringer turned on or off, but some additional options, right? Like I had a couple of you were typing in there, ask turtles, right? Ask turtles at coordinate 0, 0, move to coordinate 0, 0. And it made sense because in one level because you were trying to move 25 to all these different coordinates, and you were doing it just like the 8, 8 or 8 minus 8, but you were making a logical error because those turtles were already at 0, 0 and you didn't need to do anything, right? That was something in this causal relationship that you misunderstood. The nice thing about models is if you're making a mistake, it'll tell you. A computer has it's never forgiving. It never forgives you for being wrong. It is never polite or kind. It'll just say, wrong! 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 You'll get that sign with the stop sign and the hand holds up and says, go back to the beginning. Go back to the beginning. And that's really helpful because it's going to force you to be clearer in your thinking and more logical in your understanding of whatever phenomenon you're studying. Models can be used for analogies for other models. This actually is an example that I didn't know about, but we knew how to model. This here on the left is a model of ant movement patterns foraging around the ant nest. Over here on the left. Over here on the right, they used the algorithms that produce this pattern based on how ants move around the world, and they applied it to the flow of information on the World Wide Web, on the network. And it turns out that ants, when they're out there looking for food, actually are searching for ways to get to food. It's an optimal search pattern that has evolved over millennia of ant existence, right? Millions of years of programming has refined it into a perfect delivery system. So, in design of the World Wide Web and how packets of information are sent to all these different locations around the world, they built the web so that it follows patterns just like ants foraging. And it turns out that web traffic speeds up enormously. So that When you think about the web, you should think about ants. When you write a text message, you're sending an ant, and it's crawling all over the place looking for the best way to get to the person you sent the text, right? In such an amazing way, so that if you text me when I'm in the United States, it goes like this halfway around the planet, just being a little ant. Models certainly help you educate and communicate with other people. Building this model, most of you, some of the models that you were watching, like the ants foraging that model, termites building mounds, traffic flow patterns we looked at, all of those things, when you looked at that interface, it made great sense to you right off. It was intuitive. Now, if you crack it open and look at the code behind it, that might be a little complicated for you, right? But you understand what it's trying to accomplish by just looking at the human-computer interface. And so it helps you to learn. Now, when you see certain things happening there, you can go to the code and slowly figure out how that code's working to produce these things that you see on the interface, right? And that certainly is going to help those people. Not everybody's going to write computer code. And so trying to explain this to everybody that's never going to happen. But you can show people these patterns, and that will help them understand the phenomenon, even if they can't understand it at the detail of computer programming. Very helpful. When you go to a high school and give a presentation about your college, about your master's thesis that you're working on ethnic studies or on cultural groups, you can show them a model. And even though they won't understand the coding, they will understand the model and how your research has discovered certain things about why people do what they do. And that's pretty good. Maybe a couple of the kids will be inspired and learn to computer program. Models can serve as what our authors call focal objects. Focal objects, for me, is the thing that's the most important in making models. Models are completely literal. They take nothing for granted. They will force you to think about things that you didn't think you would have to think about when you first started with the model. You'll start building a model and you'll think it's a simple process of getting from one situation, the initiation of the world, and then the behavior of the agents. And you're going to find this is going to happen all the time, that I can't really explain what I want to explain without taking an additional step that I didn't know I was going to have to take. The computer program will not work. It's telling me that what I think is happening can't possibly be happening. And therefore, by making something the object that you're focusing on, you have to include every single element. Think of it as like you have a picture of your grandfather, a photograph, and you're trying to draw a picture of that grandfather. And you're drawing and you're drawing and you're drawing, and you thought you were done, but you look at it and you go, no, that's not right. What does it need? What am I missing? I forgot the ears. And you draw ears on grandfather. That's much better, but there's still something missing. So computer program is going to be like that. You're going to use the focal object of a photographic image of your grandfather to actually accomplish a drawing of your grandfather. Your model is going to be used for you to think about what it is you're modeling. The most important thing about that is what modelers call eliminating black boxes. A black box is a part of your argument where you're telling me some magic happens, right? You know that you start with this, it goes into this process, and it comes out the other end looking like that. And I ask you, so what happens? What's the process? How does it work? Oh, it's magic, right? This happens to this happens to that, this happens to this. My grandfather, who used to tell stories about things in order to cover up, he used to try to fool me into telling me stories about how certain parts of the world work. And so, like, if I asked him, why is the sky the color blue? He would say something like, it was magic, right? It was a black box. He can't actually tell me what are the mechanisms that work that get this to turn into this. So, for example, didn't know anything about the physics of light refraction off of the atmosphere, right? Didn't know anything about wavelength patterns in visible light spectrum. The goal of modeling will always make you open up black boxes and turn them into glass boxes, things that you can see. Third, models can be thought experiments. By thought experiments, we mean that they are the opportunity for you to imagine, to actually think about things. Einstein often daydreamed about phenomena that he saw in the world. He called these thought experiments. He asked himself, what if I'm standing on a train, moving at a certain speed, and another train passes moving in the opposite direction at a certain speed, can I define that mathematically if those trains are moving near to the speed of light? It actually turns out that time changes. Our perception of time will change as a result of that, because time is a function of the speed of light. Last, and this was the example that Professor Pan talked about, sometimes models can be used to predict. But you have to be careful about the term prediction, because, and only use the term, they output results that might predict what will happen with greater or lesser degree. Models are not deterministic. Models generate outcomes that are probabilistic, right? So your model will run and you'll be able to say something like 8 out of 10 times it produces 12 boxes. 6 out of 10 times it produces 9 boxes, and so on and so forth, right? It'll be probabilistic, increasing or decreasing likelihood. Have you seen on weather forecasts, they have models of how the typhoon is moving toward Taiwan? Have you ever seen where they have different pathways for the typhoon based on different models? So what they will do is they'll have a pathway 1, 2, 3, and each one of those will be a model to predict how the typhoon's going to move. Then they're going to say the average of all 3 of these models is the most likely scenario, because these 3 models each is useful, but the average of all 3 of them is the most likely of all. So models predict with a certain level of sensitivity, but they're not like laws of physics. Okay, so that's the reading. Out of all of that, those are the main ideas that I want to get from you. Why are you building a model? Let's talk about, before we go into some of these skills, commands, let's talk about your assignment for next week. The big grade that you're going to get for this class is a model that you're going to build in this class on your own on something that you yourself personally are interested in, invested in, that's going to help you in whatever you're studying. So, At this point, I'm trying to get you to begin to think about, based on what you know so far of modeling, what kinds of things might make a good model. And I give you 4 questions that I want you to think about and write responses to. The first one is, from all of your interests, what do you think would be the most interesting thing to build a model of? I mean, you study all kinds of things. You've been interested in all kinds of things, right? Your entire college education has been designed to expose you to phenomena and make you think about them in interesting ways, to open them up, to interpret them in more sophisticated ways. Out of all the things that you've studied, which one do you think would be good, or are you motivated to build a model for, right? Why, then tell me, why is it you're choosing this, out of all the things you could have chosen, why this one? Why do you think your specific phenomenon would benefit from building a model? So not just what it is, but why do you think it would be a good idea to make a model about this? How will this help you? Why did you choose, or what do you hope to gain from this exercise? In some way, you've identified it because you think there's something to discover that I haven't discovered yet. And I want you to say, what is it that I think I will get out of building a model? What am I going to learn? I'm going to learn why dogs walk around with their noses to the ground. Or I'm going to learn why boys in groups do more bad things than boys on their own, which is a known phenomenon, right? Young men, teenage boys, all by themselves, are usually not bad. They behave themselves. But when 6 or 8 of them get together, sometimes they start misbehaving, and there's something about being in a group that causes them to misbehave a little more. And the interesting question is, why? They have no trouble being good on their own, but when they're together in a group, sometimes things go the wrong direction. Why? So, what do you hope to gain from understanding this phenomenon by making a model? How will it further your studies, right? 3, at what level or scale or degree of detail do you want to make a model at? Do you want to understand all biomass that grows in the pond on campus? Or do you want to understand what percentage of that biomass is algae or fish, right? Or do you want to understand, want to understand the life cycle of algae to fish to insects and so on and so forth? At what level? Remember, I told you that for every phenomenon, there are different scales at which you can target to explain. I mean, I could explain to you at a molecular level why if I push on paper with my pen, here I make marks. It has to do with physics, right? Or I could explain to you the chemistry of this surface that makes it resilient and hard. Or I could explain to you the biology of skin cells that exist on the surface of any table that humans are interacting with, right? So any phenomenon you can analyze at lower or higher levels, right? And then last but not least, what kind of discoveries would you like to see as a result of your modeling? How are you going to define success? You build this model, and you learn exactly what you want to learn. So before you even start building it, ask yourself, what does success look like? It's important. If you don't know what success looks like, how are you going to build a model to produce the things that are successful. Right? So what I'm trying to get you to do is to start thinking about a model as you learn more and more about models that you're going to build for yourself that will help you. The only way that you're going to learn to use computational simulation in your life and in your studies is by actually doing it for yourself about things that you're interested in, that are unique to you. All right? And that's going to be a big part of this. I will work with you one-on-one about the models that you're trying to build, right? Above and beyond what we're doing in class. Some basic things. Some of this you've already figured out or learned, but I'm going to go through it in a systematic way, the baby steps toward building a program. All right, first things first. To make a request of an agent set, if you're trying to get this agent to act, and that's what they do, you always have to begin with a simple interrogative. The question is ask. Like, if you want Google to respond to your voice, what do you have to do? You pick up your phone. You're going to use a voice command to get Google to do something for you. What do? I tell you what we do in the United States. We go, hey, Google. And that turns Google on, and it listens to me. And then when I tell it to do something, it goes to an artificial intelligence, translates my voice into semantic program that then gets translated into code, and it'll give back to me what I'm actually asking. All right? To get turtles or patches or links to do anything, you have to use the equivalent of, hey, Google. You have to use the term ask. So in all those little commands in there, you're going to see where we put ask turtles. Or I don't think we did any ask patches, and we haven't paid any attention to links yet. But ask, and then you give commands. Commands, depending on the nature of the command, will need varying inputs. Ask turtle to do something, and then you're going to have to put something in those brackets. Whatever you're asking always goes between these two square brackets. For example, I'm going to ask the turtle, set your shape to an airplane. That means stop being an arrow, which is the default shape, and become an airplane. And it turns itself into the shape of an airplane. Ask patches, sprout turtles 1. Basically, I'm telling this turtle or this patch here to grow a new turtle, and it adds a new turtle to the world. Sprout means to pop up out of the ground, a new turtle. So those are two examples of two commands. Ask turtles, and then always give it commands and other information between these brackets. It's how you get anything done in this world. Movements, you've already learned a couple of movements, right? You've been using right or right turn, some number of degrees, or left turn, some number of degrees. There are also, you've used commands like forward, go forward, FD. You can either write the whole word forward or just FD, or back or BK. That means it goes back a number of steps, right? Those are all movement commands. You've been using those as well to get your turtles to move around. You also used, in one of the models we just built, the command move to. You asked a subgroup of your turtles that you created to move to a new set of coordinates, which were 8, 8. Right? You're telling the turtles, wherever you are, jump to the coordinates 8, 8. Move to it. You can also ask it to just jump. Right? Jump and move to are kind of similar. Under certain conditions, jump may cause different outcomes as opposed to others. So you say jump, and then you tell it how far. You type that in, and your turtle will jump to a new spot. Or last one to move is set XY. The term set XY means, hey turtle, ask turtle, colon, set, which means, remember your X coordinate and your Y coordinates, those are variables or properties built into the turtle. So you're asking it to reset those variables to new values, to new numbers. So if I say set your XY to position 8, 8, it'll cause those turtles to move all to 8, 8. So move to a new spot, jump to a new spot, or reset your own internal coordinates based on some new spot that's your target. 3 different commands for movement. So here are some features. This will add some, some quality to your experience of modeling. Escape. I want you to go up here to the Tools menu. Click on the Tools menu. We haven't opened this menu yet. You should get a drop-down box, and I want you to go first off to color swatches. A color swatch. And click on that. Color swatches are just little patches. If you've ever gone to a paint store and it'll give you a bunch of different samples of small squares painted in different colors, and you can take those home and hold them up to your furniture to see if the paint matches your furniture color, those are swatches. This is the total range of colors that NetLogo can handle. NetLogo has built-in colors that are also given numerical values, starting with the color gray to red to orange to brown, yellow, all the way down to pink. Now, the default number on this color swatch is always going to be the 5 unit. So 5, 10, 15, 20, 25, 30, so on, up and down here. Actually, I'm jumping 5, 15, 25, 35, 45. Those are the basic colors. But you can choose other colors by indicating any one of them. And the easiest way to choose those is to just take your cursor over the color swatches, whichever one, click on it, and then it will, down here, and copy the color selected right there. It will show you what color you picked. So all you got to do is click and point. So click up there on that pinky thing. It's basically red, which is 15 plus 1 equals 16. So you can select and set the colors of all your agents. Let's see here. So I'm going to go, let's do code. And up here somewhere, I set the color of my car to red. Right now, I want to set it a new color, and I don't know what the color blue is. I can look it up in the swatch, or I'm just going to click in there, eliminate red, and put blue, which is a basic color that NetLogo understands. Now, if I go to the interface, setup, I'm going to have 2 blue cars. This is going to be important because you're going to create little groups, agent sets, right? You have 1,000 turtles, but 200 of them are green, and 200 of them are blue, and 200 of them are black. That way you can ask subpopulations to do things, you can force them, you can get them to interact with each other, you can have properties that one group has but another group doesn't have. By changing the color of things, you distinguish groups of turtles by a new variable, and that allows you to find them. The other thing in this tools dropdown is the shapes, turtle shapes editor. You see that there? You have color swatches, and now you have turtle shapes editors. Click on that, and you will get the default menu of all the shapes you can give to turtles. Turtles are their basic names, but turtles can become hunter-gatherers or mammoths. In the model I was working on, I had woolly mammoths and I had hunters. But say you're working on traffic patterns and you want cars, or you're working on butterflies that are pollinators in a field of flowers. You can use butterfly, you can use fish, house, maple leaf, so on and so forth. All of those are in there. Those are your default shapes. Any one of those, I'm not sure how many there are, maybe 30 or 25 or something. But there is also a bigger library. If you go down to the bottom and you click Import from Library, down at the bottom, it will give you a much larger selection of all kinds of shapes that don't come automatically built into NetLogo. So here you have things like acorns and footballs, those weren't in there, books, cactuses, caterpillars, cows, happy faces, ghosts, a sealed letter and an open letter. I suppose if you're doing information flow, a mortar and pestle, different kinds of police, like police officers, lumberjacks, and college students, sharks, so on. Each one of those, you click on one, like a squirrel, and then you click on import, and that will then pull it into the shapes editor that you use for your model, and that shape will then be available for you to use in your model. If you don't import one of those shapes first, you won't be able to make anything that shape in your model. The way in which you do that is, let me see, if you go to your code and I set the shape a car, but suppose I don't want it to be a car, I want it to be a cow. I set the shape cow, interface, set up, and now I have two blue cows running around. All right? Because this model is now about dairy farms and not about traffic patterns. Okay? The one thing about setting the shape is you have to put whatever shape you set your turtle, you have to put it in quotation marks, because that value in there is actually what computer calls a list, or not a list. What do they call it? I'm blanking on the term. A string. So it actually has to be demarcated off to indicate that it's a model image. Oh, and last but not least, forgot about that. This will be fun for some of you. If in the Turtle Shapes editor, there's nothing in there that you like, either in the original editor or in the Shapes editor, you can make your own. So here is a design environment for you to build your own icon. I don't know what I'm making. A ladybug. Something like that. Nope, don't save. Yeah, I want to cancel. So you can make your own icon if none of those suit your purposes. This gives your model, it's not a big deal, but it'll give your model a little pizzazz. It'll look nicer, right? And you enjoy modeling more if you can make it look nice. Okay, how to work with colors, how to work with shapes. Look here, we'll talk about how to set colors. So ask turtles, and then in here, remember that's the command block, set the color that you want to set it, red or green. Ask patches, set the P color, red, green, whatever. Note the difference between color and P color. Color is a variable that only belongs to turtles. P color is a variable that only belongs to patches. P, patches, C, or color for turtles. Anything that's patch related oftentimes will have a P in front of it to distinguish it from the variables that turtles have. Okay? And we did the shapes editor. At least in some of the code, when we were telling turtles to move forward or move left or right, actually, I don't think I gave you any of these yet, now that I think about it. We'll use them in the upcoming models that we're going to build. You have the most important, probably the most important single command structure in computer programming. It's called ITTT, which stands for, if this is the case, then do that. So what it's asking is, it's a conditional. If a certain condition is met, then do something. Put a little differently, hey turtle, check this out. If you see it, then do this. If you don't see it, don't do that. Right? So you have a conditional that is the most important example of coding. Here we go. Ask turtles if you are standing on a patch, and it knows it's a patch because it says P color. If you're standing on a patch with your P color equal to green, then move ahead 1. If the color is not green, that's implied by that, all other colors, then don't move forward 1. So if condition met, do this. Here's another example. If P color equals yellow, right turn 90 degrees forward 1 step. All right? You'll use this all the time. If, then. If this, then that. Always in here for if, what it's doing is telling you to look at the world and tell me whether or not a certain condition is true. That is called a reporter. That means that a certain snip of code, a certain little piece of code, reports to the turtle that's looking at something. Right? So I'm telling the turtle, I'm the God, I run this world, and I tell the turtle, hey turtle, if this condition is true, then do something. Right? We use these all the time in computer programming. If then, if then, if then. The only other one we use about as much is if else. Right? So here, that one there is the reporter block. It's telling the turtle that yes, the P color here is yellow. Or yes, the P color here is green. So if then, if this, then that. I'll give you some examples of that when we're making things. Another thing about computer models is that they have the ability to inject into this world various random values. So in actuality, computers cannot pick things that are random. Computers are actually deterministic. They follow ironclad mathematical rules. They can't kind of guess something like this or that. They don't have freedom in that way. So what we are technically generating in any computer program is something called a pseudocode. A pseudo-random number. For example, if I ask it to generate a random number, it might have a little subroutine written into it to pick the number, to pick the time in minutes when this command is sent to the computer, divide that by the hour that it currently is, and add 17 to it. Right? So if I press go right now, it's going to have a certain set of numbers, and then 30 minutes later, it's going to have a very different set of numbers. What determines whether or not it was this or that? I suppose somewhere, somehow, there were some logical rules why it came out that way, but the truth is, for all intents and purposes, in our program, it's a random number. And that's how computers interject into their models a certain amount of chance. There are different ways of including randomness. For example, if you want a range of random numbers, like I want a random number between 12 and 25, ask Turtle. Forward, random, random 17 plus up to 25, so I'm going to put plus 8. All right. Pick a number, a random number between 17 plus 8, which means it's going to be any random number between 17 and 25. Right? So there I'm picking a range. If I just put forward random 12, then it's going to move forward a certain any number of steps between 0 and 12. And it generates a random number to do that. This is important because there are lots of things in the world where you don't really know how far someone's going to move. Like a dog is searching for a piece of food. How many steps in one direction will it take before it turns another direction? You might need a random number to be assigned to that dog's movement. Right?
So I still not understand how computer do the random thing.
How does it do it?
Yes.
Okay, so I'll use the clock number or example that I had. All right, it is I push whatever button it takes. It's the to go button. I'll push that button in for a NetLogo model, and I happen to push it at 13, 12, 37 seconds. Oh, 77. 37 seconds. The computer can take the number 12 because it picks a minute, because it happened to have, I happened to say execute at this time. It picks the number 12. If I push the button 2 hours later and that number is 14, then it'll pick that out of the clock. There's no deterministic reason why I would start the command executing in one way as opposed to another. Now, we say pseudo-random because in reality, that number is not really random. If we studied it closely enough, we could explain the mechanisms for why it came up, right? I mean, the truth is, if you're flipping a coin to do statistics about random numbers, if I understand in enough detail everything about the physics of that coin and flipping, I could remove randomness from that, right? Random and probability and statistics are only necessary if we can't measure the world adequately. That's why they're so useful, because we never measure anything with total precision. All right. So, but for the purposes of the program, you don't have to worry about how it comes up with random numbers, just that you're injecting a certain element of chance into the model. Different ways. So, set a range of numbers, the number x plus a random additional set of numbers. So if this number is 17, and then add an additional random 8, my random number is going to be, it could be anything between 17 and 25. All right? Random coordinates. I'm going to say jump to some random x coordinate in the world and some random y coordinate in the world. That means, like, the movement commands are jump, and the x coordinate is a turtle coordinate, so it's going to jump to some x coordinate in the world. This is a turtle, some random y coordinate, within the limits of the environment itself. So remember, the default size is -16, 16, -16, 16. It cannot generate, if you're asking a random x coordinate, it's going to be a number between -16 and +16. It can't jump out of the world that you've built for it. If you want to pick any random direction, you tell your turtle, head off in some direction that I can't predict. For whatever reason, you always use, I always use, and I would recommend this for everybody, it's probably the most frequently way to get a random direction. Turn right some random number up to 90. So what would be a random number up to 90? 47. Then turn left some random number, which would be what? 94. No, I can't, I only got 90. 84, right? So it turns right, 37, and then left, 94. Right? Where's it going to be? It's going to be here. If it went right turn 90, and then left turn 90, what happens? It goes right back to where it began. Right? So 90 and 90 is just going to, I'm having it turn right, and then I'm having it turn left. And because both of those values are random, basically that gives it a wiggle. And you can't predict where the wiggle is going to let it land. That means now it's going to head off in a new random direction. If you want to, put a bunch of turtles in the world, have them spread out around the world, and then give them the command to turn right, random 90, turn left, random 90, and then forward 2. And they're going to go like this. And put the pen down, and you'll have all these turtles drawing little different colored lines all over your, going in random directions. No pattern. And then one more command you're going to need for the model coming up, N of. N stands for number. And so N of always means that you're choosing a specific number of turtles. We'll just leave it at turtles for now. N of, say I have 100 turtles, and I want to pick out 25. N of 25 turtles. So ask N of 25 turtles. Jump. Ask a random group of 25 turtles out of these 100, jump to coordinates 8, 8. Now remember, you were picking turtles based upon their who numbers, and you were bunching them into 25. Right? Now what I'm doing is picking a random subset out of all those 100 turtles and just telling them to jump to those coordinates. It would do exactly the same thing as calling the who number, which is how you accomplished it in the spirograph exercises. That's the N of command. N of, which means number of how many? 25, 10, what have you. I think we only have a couple more. We're already here to the first exercise. I'm just going to describe this particular exercise in the time we have left. It's just about 10 minutes. And this is what I'm asking you. Based on all the information, all the commands I've given you, you know how to make this. I want you to write a model with 100 turtles in the world whose color is red. I want you to make the background color of the world green. The entire world needs to be green, and have the turtles jump in random directions for a random set of distances. Okay? Maybe I'll add one more thing to it. I think you ought to try to make, in the shapes editor, since you've learned the shapes editor, and shape is bean-like. Okay? Go into the shapes editor, look around, see if you can find something that looks like a bean, like a lima bean, or some kind of bean like that. You know what Mexican jumping beans are? Have you ever seen them? Mexican jumping beans are little bitty beans, like seed pods, and they have a worm inside of them. And you buy these things as kids, and the worms inside of the beans move real quickly and spasmodically. And so if you hold these beans in your hand or you sit them on a table, they start jumping in all different directions. Right? So what you're going to be doing is building a model of turtles that act like Mexican jumping beans. Write a model with 100 turtles whose color is red and whose shape is bean-like. Make the background of your world a color green. See, I'm getting you to use shapes editor and color selector, and have the turtles jump a movement command use random values in random directions, right? And in random distances. So we have 9 minutes left of official class time. If you want to work on the model, first start trying to do this, work away, and I'll stay here and look at what you're doing or help you. If you want to go, then this is, along with writing that essay, I want you to try to create this model before class the next time. The Mexican jumping bean. If you can't do it, fine, we'll work together on it. But I want you to try, because you actually know how to do this already.